before the kind of introduction, Mr. Turner. So it's a pleasure to be here with you. Can you listen to me well in the back? Yes. Okay. So today I will tell you a bit about this zero-dimensional material that you might not know, which is carbon nanoonions. Funny name to start with. I will talk about some of the material properties. The talk is going to be short, but introduce to the material, how you can synthesize it, and then some results regarding inkjet printing of this material using ethanol-based solutions. Okay, so ethanol-based solvents. Just a quick introduction of my institute. So the International Iberian Nanotechnology Laboratory is a joint venture between the Spanish and the Portuguese governments. It was born in 2008, and since then we have been growing, and we now have 24 research groups working in a variety of fields, from micro and nano fabrication, spintronics, environmental health monitoring, and food safety. We are here in a flexible electronics conference, and you know this exciting field started in the 70s. This is to motivate you about different manufacturing schemes. So in the beginning, when people started depositing thin films, for example, morphosilicon TFTs and solar cells on flexible substrates, this was the beginning of flexible electronics. And most of these fabrication processes were based on clean room techniques, so thin film evaporation, chemical vapor deposition, lithography, etching, and so on. Nowadays, we are going towards additive manufacturing. So I have here some examples we already heard in the previous talk. I would like to highlight, for example, screen printing, flexography, spray coating, and inkjet printing. Inkjet printing, everybody knows it because it's readily available in the supermarket. You can buy your printer and print stuff at home. But that is the graphics application. Nowadays, manufacturers have been working on newer inkjet heads that can work with higher viscosity inks, and this starts opening doors for the deposition of functional materials. So some of the advantages of inkjet printing you already know. Non-contact technique. It is a digital technique. You don't need to fabricate hardware to keep always the same production. So it's good for prototyping. And with new heads that can operate at tens of kilohertz, so firing rate, generation of drops, you can work up to meters per second. So this is actually becoming fast, and it can go into industrial production in a roll-to-roll fashion. Some examples of materials that you can find on the market. The most common are the metal nanoparticle inks, silver, gold, copper. You can also find carbon black inks, the electric and piezoelectric commercial inks. If you're interested in starting this type of processes, I invite you to check out some of these manufacturers. But I'm not here to talk about industry. I'm not paid by these companies. So in the literature, we can start finding more exotic materials towards these functional materials. We can find inkjet printing of graphene, carbon nanotubes, fullerenes, MXNs, and so on. And here I want to talk about these carbon nanoonions. These are essentially multi-layer fullerenes, so only carbon material. And for comparison, and to have a little bit of a discussion in terms of the process development, I will also show you printed test structures made of silver. Okay, I printed also this commercially available silver nanoparticle ink. Carbon nanoonions were first reported in 1992 by Daniel Ugart. We have here on the right the original Nature paper, transmission electron micrographs, where you can see the spheric shape with concentric layers. These are relatively large carbon nanoonions, around 50 nanometers of diameter. You can do them smaller, down to 5 to 10 nanometers. The interlayer distance is essentially the same as graphite, around 3.3 angstrom. The density of carbon nanoonions is slightly lower than graphite, standing at 1.6 grams per cubic centimeter. Because you find this in the powder form, no surprise, it has a large surface area, close to 1,000 square meters per gram. Regarding the standard synthesis methods, if you want more, I have an extra slide in the end. You can ask me. There are many people in the literature have synthesized these in tens of different ways. The most common ones to obtain small carbon nanoonions is by nanodiamond annealing, and for larger CNOs, typically by arc discharge. Now, to our specific work, we used an alternative synthesis technique, which has been reported in the literature. And because of its simplicity and low cost, and no special purification, this looks a bit exotic, but it works. So essentially, you have an oil. In our case, it was clarified butter, and you just use a lamp. 2 centimeters away from the flame, you have a copper collector. You collect this carbon soot. You centrifuge it and then resuspend it in a non-concentration, sonicate it a bit, and we can obtain an ethanol-based suspension which stays stable for weeks. So it doesn't settle. You can work with it easily. So for a concentration of 6 milligram per milliliter, we could obtain a suspension with a reasonable viscosity and surface tension to work with commercial piezoelectric printheads. Upon TEM inspection, so this synthesis method allowed us to obtain carbon nanoanions with a narrow size dispersion in 30 and 40 nanometers. And here on the right, you can see once again, perhaps it's a slightly better quality than before, I hope. The diameter of the carbon nanoanion and the internal structure, the layered structure. Our methods. So for printing, for this first prototyping, I used a single nozzle piezoelectric solution. It has a 25 micron nozzle. The average drop size is around 50 picoliter. However, I optimized the drop generation condition using a microscope camera and a stroboscopic illumination system, which is synchronized with the drop generation. For printing, precision XYZ stage, nothing special. For the actuation of the piezoelectric dispenser, a bipolar pulse, we can control both the amplitudes and the duration of the pulse that we apply to the piezoelectric printhead. And then using this microscopic system, because we know very well what is the time interval between these stroboscopic flashes, we can measure the drop velocities and also the volumes. So now, as I told you, I printed and did this development for silver nanoparticle ink. Here on the left, this is a commercial ink. And here on the right, our ethanol-based suspension. This silver ink is water-based. So what I want to show you here is the drop velocity in black and drop volume in blue. We could achieve conditions that do not generate satellite drops for the printing, so well-controlled conditions. For the silver nanoparticle ink, the drop volume is between 50 and 90 picoliters. We can control it. We work with the smallest volume possible for the best resolution. And for the carbon nanoanion ink, between 50 and 60 picoliters. The average drop around 2 meters per second, causes no splash on the substrate. The substrate was PET, polyethylene terephthalate. Okay, so to print, what we need to do, we need to have a substrate. I was saying we used PET. And for electronics, we want to have continuous structure. So we want to be able to print a continuous line. If for a fixed firing rate, here it's very low, as I was saying before. Depending on the particular print head, it can go up to 10, 20, 30 kilohertz for state-of-the-art heads. Okay, this is just an example. We can scale this up to kilohertz in our particular case. So we optimize the print velocity in terms of the stage printing in order to obtain homogeneous lines. Our line width for silver nanoparticle ink on PET substrate was around 110 micron. For the CNO, larger because of the interaction between the ethanol and the substrate, so it spreads. No surprise. Then we try to print multiple times in order to try to increase our thickness, because depending on the device, if you want lower resistance, you need to print multiple times to obtain a larger thickness. So this is the case for the carbon nanoanion ink. You can see clearly here, as we increase the number of passages, we have higher optical density. But the results for the water-based silver nanoparticle ink are quite different. So this is after sintering. We measure the thickness using a contact profilometer, measure the thickness of these lines. What we see is that for more than 2 passes, the volume is excessive, and we start having these disturbances in the line, and it gets into these random shapes. But if we do just 2-pass printing, as you can see here on the right, you can keep their width at around 110 micron. All right. For this carbon nano-onion, this is ethanol-based. The solvent evaporates very quickly, almost essentially before you start the new pass, it has already evaporated. And you can increase the thickness of your printed layer without causing any enlargement of your features. So we printed these test lines. We attached some wires using nickel paste, and then we did some electrical characterization as a function of temperature and humidity. So we used here a climatic test chamber at a constant relative humidity around 50%. I scanned the temperature from 20 to 90 degrees Celsius and back. That is essentially the result. So we have here with the triangles, the series for the silver printed test line, and here for the carbon nano-onion test line. So they have different and opposite thermal coefficients of resistance. Silver is a metal, so due to increased kinetic energy, it behaves as a metal. We have lower conductivity with the temperature, and the carbon nano-onions essentially behave like graphite, which around room temperature and up to 500, 700 degrees Celsius. So the resistivity decreases. So we extracted our temperature coefficients of resistance, and at 25 degrees Celsius, here the volume resistivity of our materials. Silver nanoparticle standing at around 10 to the minus 4 ohm meter, which is as specified by the manufacturer. So this is approximately 2 orders of magnitude larger than the bulk material. And in our case, we could not use a very high sintering temperature because of the polyethylene terephthalate substrate, which does not support it. It starts softening too much. The carbon nano-onion ink is pretty resistive. So it's not a good idea without using other additives or other strategies to try to replace our metal lines with carbon nano-onions. But they have other roles. Then we tried to keep a constant temperature, 40 degrees Celsius, and sweep our humidity from 20 to 90 and back. And what we see is that the silver nanoparticle here on the top essentially changes by less than 10%, while the resistivity of the carbon nano-onions went down by an order of magnitude. This is quite interesting. So we have this porous material. We have reports in the literature of interaction with gases. So this points towards applications in gas sensing, humidity sensing, and other sensing applications. And in the synthesis, if we can also include functionalization-specific chemical moieties, we can probably be more specific. So to conclude, I presented you here this very simple flame synthesis technique, which I hope I convince you can allow you to obtain this monodispersed suspension. Because this ink is ethanol-based, we can do multipass printing without degrading the resolution. Yeah, and this is it. So that although the carbon nano-onion ink is quite resistive, we can think about introducing either conductive polymers or other additives or even other materials with different sizes to improve the conductivity between individual particles. Thank you very much. If you want, I can share this reference.
Thank you very much. Thank you.